First thing we're going to look at today is reciprocal graphs, which brings up this idea of asymptotes. So a little bit more detail about asymptotes. So when you're drawing your asymptotes, they should always bend towards them. Curves never cross a vertical asymptote, because vertical asymptotes are exclusions in the domain. So there's no way the graph could ever go there, because that x value is not in the domain, so you can't substitute it in and get a value. As opposed to the horizontal and oblique asymptotes, they can cut those, because that's what's happening out of the extremities. So x is approaching infinity or minus infinity. It's just telling you where the curve's heading towards which line or which curve. So it can cut it closer to zero. And when we're talking about infinity, any number really is closer to zero. Polynomial division. So if you've got a fraction where there's a polynomial on the top and the bottom, you do the polynomial division. You can always divide it up into quotient plus remainder over divisor. When it's in that form, that tells you a heck of a lot of information. Okay? So the bottom of the fraction, that's going to find those domain problems. So that's where the vertical asymptotes will be. So we look at the bottom of the fraction, it tells us about the vertical asymptotes. Now the quotient turns out to be the horizontal or oblique asymptote. So that's where the curve will head to out of the extremities. And then the top of the fraction, this is where we can find out whether or not the curve does cut the horizontal or oblique asymptotes. All we've got to do is solve that top of the fraction equals 0. If we have a solution, then that's where it will cut the horizontal or oblique asymptote. So putting it in that form gives us a lot of information. Let's try it with this one. Now I've factorized it all to make life a little bit easier. So when we look at this particular curve, I can say, well, let's do the polynomial division, because you'll notice it is a quadratic on top and a quadratic on bottom. So in order to do the division, I need to expand it out. So the bottom's actually x squared minus 1, the top's x squared plus x minus 6. So x squared goes in x squared once, and we end up with a remainder of x minus 5. We've done our polynomial division, which means we can rewrite this function as 1 plus x minus 5 on x minus 1, x plus 1. So that's telling me a lot about this graph. The x-intercepts, I'll go back to the original function for the x-intercepts, because that's when y is going to equal 0. It's easier to find the x-intercepts when you've just got one fraction, because if you've got a fraction that equals 0, it must be the top of the fraction that equals 0. So that tells me I've got x-intercepts at -3 and +2. So I'll plot those in. The y-intercept, well, again, that's an easy one to find. We just got to substitute in x equals 0. We end up with 6. I'll plot that in. Vertical asymptotes. So the bottom of the fraction will tell me that. So x can't equal plus or minus 1. We know we're going to have vertical asymptotes there. So let's draw those in. We're going to have a horizontal asymptote in this case. If it's a constant, it'll be a horizontal asymptote. If it's some function, then that's when we get the oblique asymptote. So horizontal asymptote at y equals 1. The next question is, does it actually cut it? And in this case, yes, it does. Because the top of the fraction, x minus 5, that can equal 0. And it'll equal 0 at x equals 5. So I know it'll actually cut that horizontal asymptote at x equals 5. So now the challenge is to draw this curve. And that's where the idea of it'll always bend towards the asymptote comes in handy. I know if we work from left to right, I can't cross the horizontal asymptote. So I'm either going to be up here like a hyperbola or down the bottom like a hyperbola. But we know it goes through -3. So we know it must be down the bottom like a hyperbola. Now we have a look at the next section in between these two asymptotes. I've got to go through the point 6, but no, I don't cut the horizontal asymptote. So I can't go down like an upside down parabola. I must go up. Then we get to the last section. It's got to go through 2. So it'll bend towards the asymptote, come up through 2. It'll cut the horizontal one at 5. And then at some point it must turn and come back down, because it's then got to turn towards the asymptote. So let's have a go at drawing that. There's the first section. second section, this is where it gets a bit dodgy. Yeah, got a little bit bumpy there, but hopefully you get the idea. It's got to come through that point and at some point turn and then bend towards the asymptote. So interesting little graph over there on the right. But all of that information I got just by doing the polynomial division of the fraction. Let's try another one. So this time I've got a cubic on top and a quadratic on the bottom. Let's do the polynomial division. So x squared and x cubed goes x, and we get a remainder of minus x squared plus 5x plus 2, so I can keep going. X squared into minus x squared is minus 1, and my remainder 4x minus 4. So I could rewrite this fraction as x minus 1 plus 4x minus 4 on, well, x plus 2, x minus 3. Let's read off our information. X-intercepts, I'll go back to the original one. Top of the fraction must equal 0. So I know we've got them at minus 1, 1 and 2. Y-intercept, sub in 0, we end up with minus a third. So I'll plot that point in. Vertical asymptotes, bottom of the fraction. So we can't have negative 2 or positive 3. Let's draw those in. In this case, we've got an oblique asymptote. So it'll be y equals x minus 1. Let's draw that in. And then I can use the top of the fraction to tell whether it will cut it. And in fact, I already know, because you'll notice that oblique asymptote is going through what we've already identified as an x-intercept. And I can confirm that because if I solve 4x minus 4 equals 0, yeah, I get x equals 1. So it's definitely going to do that. Well, what is this curve going to do? Okay, start from the left. We're either going to be stuck in this little triangle here, or we get sort of like a hyperbola going up. But there is no x-intercept here. So I must be like down in that little triangle there. Now, the middle bit. Did I do the middle bit next, I wonder, or did I just go to the right-hand side? Because the right-hand side is going to have the same issue. You'll notice I've got no x-intercept here. So I must be in this triangle up the top here. I'm stuck in there. Oh no, I did the middle bit first. All right, I've got to go through all these points and I've got to bend towards the asymptotes. Now logic says I've got to do it this way because I can't start down here because I would have to cut the oblique asymptote. And we've already said it'll only do that over at 1. So I can't get to negative 1. So I must have started up here. And so that's how I started the curve. Come down, go through minus 1. I know it goes through minus a third. It will cut at 1. It must turn to come back through 2 and then bend towards the asymptote. And then there's the last little bit there. It will be in that triangle. So just doing a simple polynomial division, we can actually draw some really interesting graphs. Now, where those turn precisely, once we know about calculus, we'll be able to locate the exact position of those. But that's to come later. So how do we draw a graph of a reciprocal function? If we want to turn the curve upside down, what to look out for? The original function, well, if the original function is equal to 0, when I turn it upside down, I'm going to have a problem because I can't have 0 on the bottom of the fraction. So it'll be undefined. It'll turn into a vertical asymptote. Okay, here's a random graph which I've tried to put every possible feature I could think of there. I've got a horizontal asymptote, I've got a vertical one, I've got x-intercepts, I've got turning points. So we're saying this original graph, where it cuts the x-axis, I'll end up with asymptotes. So I'll draw those in red. Right, we know they're there. The reverse should happen. If the original graph is going towards infinity, so it's going towards the vertical asymptote, then when I turn it upside down, it should go towards 0. So we will get an x-intercept, sort of. So the original graph, here we go. Up here, it was going towards the infinity. So when I turn it upside down, I'll get an x-intercept, sort of. Now I say sort of, because actually what we get there is a point discontinuity. It doesn't exist. Because remember, that x value is not in the domain of what we're turning upside down. Now when we turn upside down, it can't magically go in the domain. So the curve will look like it's cutting there, but it'll have a point discontinuity. So we have our x-intercept, sort of. Now, 1 is always a good point, because if you turn 1 upside down, you get 1. So I know wherever the original curve has a y value of 1, when I turn it upside down, it's still going to be at that point. So identifying y equals 1 is good. Same with negative 1. The diagram's a little bit dodgy, but that's meant to be negative 1, where that's turning there. So turn it upside down, that'll still be negative 1, and over here that'll still be negative 1. My horizontal asymptote, well, it's smaller than 1 on the original graph. If I turn a number smaller than 1 upside down, I'll get a number that's bigger than 1. So my asymptote moves to be above 1. If the original curve is going up, then the reciprocal will go down, and vice versa. Okay? The sign's not going to change. Turn a positive number upside down and it'll still be positive. Turn a negative number upside down and it'll still be negative. Okay. So what I'm now doing is identifying where the curve exists to get a feel for how I'm going to draw this graph. How did I identify it? Again, 1 is the key. Because over here, the original graph is below 1. Turn it upside down, it'll be above 1. But hang on, the original graph did not cut the horizontal asymptote. So therefore, when I turn it upside down, it still won't cut the horizontal. So I know I'm in that section there. Okay, let's go to the next bit. The next bit, it was totally above 1. Now it's going to be totally below 1. But it's going to stay positive. Turn a positive upside down, it'll be positive. It's going to end up going through our pretend x-intercept, so it can then get into this section. Now when I say above 1 and below 1 here, forget about the negative. I'm just saying it's below 1, so it goes above 1. Then we get to the next section. It's above 1, it goes below 1. Okay. Then below 1, above 1. Above 1, below 1. Below 1, above 1. And then we get to this section. Above 1, below 1. And then the last bit, it's below 1, but it's also below the horizontal asymptote. So when I turn it upside down, it'll go above the horizontal asymptote. So that's where my new curve exists. I should be able to get a picture from that. This will make more sense once we've done calculus. Okay? But when you actually, what we say, differentiate, if you differentiate one on function x, you end up with minus the derivative on the function squared. So stationary points, wow, there's a lot of theory we know nothing about yet. Stationary points are when the derivative is equal to 0. So when I've turned it upside down, the derivative is on the top of the fraction. It will still equal 0. That's proving what I'm basically saying here. Any stationary point or turning point will still be a turning point at that x value. The y value might change. So all right, I know this curve will turn at that x value and that x value, those things. Okay, so I'll plot that turning point in, and there is the reciprocal graph, the red one there. Okay, so it goes through all those regions, bends towards the asymptotes. I've identified particular points it goes through. Now obviously that graph I've drawn there was a little bit complicated because I had so many different features happening at once. But they're all the different ideas that we would look at. I'll get rid of the old graph so we can see it in all its glory. There it is. Isn't that lovely? Okay. So 5C is on this idea of asymptotes and turning curves upside down. Not a lot of questions there to do, but we'll get the idea.